Hey guys, Mr. B here. In this video, we're going to be going over chapter 4.3 on isotopes and how we distinguish between different types of atoms. So let's get started. Now, most of you probably, of course, are familiar with atoms and the different parts inside of them as from previous chapter sections, but you probably don't realize that atoms actually are different from one another, even if they are the same element. And this is what we're going to be talking about today. So first off, we're going to talk about what makes one atom of one element different from another element, right? What's the difference between a gold atom and a copper atom? So first off, each element is distinguishable based upon the number of protons they have in their nucleus. Okay, this is a very special term. We call this the atomic number. So this is what will make copper different from gold, different from carbon, different from oxygen, is how many protons there are in the center of the atom. Okay. So if we look at this chart here, the periodic table is primarily organized by increasing atomic number. So hydrogen is element number 1. It has 1 proton in its nucleus. Helium has 2 protons in its nucleus. Lithium has 3 protons. Beryllium has 4 protons. So every time you add a proton to the nucleus of an atom, you are changing what element it is. Now the number of neutrons, that can change between atoms, and that doesn't affect which atom or which element it is. We'll talk about mass number as well, and number of electrons. So one thing to note, and we will learn more about electrons in further chapters, but for now, in any atom that is neutral, that does not have an electric charge on it overall, the number of protons and electrons will always be equal to each other. Okay, so basically what I'm saying is if you have an atom of any element, let's say for example in this case carbon, right? Carbon has 6 protons. As long as that carbon overall on the whole thing has no electric charge on it, it will also have 6 electrons. And that's because the protons are positive, the electrons are negative, and positive charge and negative charge will cancel each other out to essentially give you an atom that has no charge, right? That's neutral. So again, we'll learn more about electrons later, but that's a pretty big thing to know. So that basically what this is saying is if we know the atomic number of the element, not only do we know number of protons, we also know number of electrons. Okay, so protons and electrons are always going to be the same, basically, as you can see here on this table. Neutrons will change. We'll talk about those in a little bit. So, all right, let's take a look at an example question here, and we're actually going to erase this little picture. That way we have some space to write. So let's insert a text box. So it says the element nitrogen, and it has a symbol of N, is shown here in liquid form, which I just erased, and has an atomic number of 7. How many protons and electrons are in a neutral nitrogen atom? Okay, so here again is that word neutral, as I said before. Neutral meaning that it has no charge. Okay, so first off, if the atomic number of nitrogen is 7, okay, so which they're telling us in the problem, atomic number is equal to 7, then by definition, atomic number is number of protons. Okay, so protons in this case is going to be 7, because that's what atomic number says. And if the atom is neutral, so it has no electric charge on it, that also means that it will have 7 electrons, okay? Because positive protons, negative electrons, those two will balance each other out. So, okay. Again, there's some practice problems. These are going to be at the end of the quizzes that you can do on your own. So I'm going to keep going, talk about information. So other than finding number of protons and electrons, let's talk about neutrons, because those are really the ones that are a little bit more challenging to find. So the term we're going to be talking about is called mass number. And so the mass number of an element, or I should say the mass number of an atom, is going to be the protons and the neutrons added together. Okay, now the thing to remember here is when we talk about mass number, remember that protons and neutrons are the 2 particles that are inside of an atom that have any kind of mass. Okay, this is from the previous chapter section, 4.2. Remember that electrons are very, very, very small. So when we talk about how massive an atom is, the only 2 particles that make up the mass are the protons and neutrons. We ignore the electrons. So the mass number basically comes from taking the number of protons plus the number of neutrons and adding them together to give us a mass number. Okay, so mass number is essentially a sum. It's a sum of 2 numbers, protons plus neutrons. If then we want to find how many neutrons are in the nucleus of an atom, what we would do is we'd find the difference between the mass number and the atomic number. Okay, and again, I will just, to remind us here, let's even put this in red, just to remind us. Mass number is protons plus neutrons, and the atomic number, by definition, is just protons, okay, just number of protons. So if you take the mass number minus atomic number, we get number of neutrons. And they have a little equation down here for you. So now one way that we will write the notation for atoms is something that looks like this. Okay, now this is what we call isotope notation. That's what this is. Basically what we do is we have a chemical symbol. I don't know if I can type on this here. Let me see if I can insert another text box. That might make this easier. So we have the element symbol, okay, which is going to be, of course, a 1-letter or 2-letter abbreviation from the periodic table. Then we have a big number, which is going to be written up above. That is the mass number, okay? So the mass number is the number of protons plus neutrons. And then we have a smaller number down underneath, and the smaller number down underneath is the atomic number. So that is strictly only number of protons. So if we want to find the number of neutrons, and we have a atom written in this kind of notation, all we have to do is just take the larger number on top, subtract the bottom number down below, and that's how many neutrons there are. Okay, pretty simple subtraction problem. So let's take a look at another example problem here. So it says, how many protons, electrons, and neutrons are in each atom? All right, so again, let's insert a text box down here. We can do some typing. Let's change our font to red. Let's change our font size to 18. Okay, here we go. So beryllium, atomic number is 4. So that means that it has 4 protons, because atomic number is, by definition, number of protons. That also means it has 4 electrons, because again, as long as the atom is neutral, which I'm going to assume in this problem they're neutral because they're not telling us otherwise, and we haven't learned about anything otherwise, they're going to be the same. Okay, so protons and neutrons are going to be the same number. And then as for number of neutrons, protons and electrons will be the same. As for number of neutrons, we're going to take the mass number, which is 9, minus the atomic number, and that will tell us how many neutrons there are. Okay, and that's it. So that's simple. So for neon has an atomic number of 10, so that is 10 protons. That also gives us 10 electrons. Mass number is 20, so 20 minus 10, that gives us 10 neutrons. And then as for sodium, let's write Na for sodium. Atomic number being 11 means we have 11 protons. Also means we have 11 electrons. And if the mass number is 23, 23 minus 11, that gives us 12 neutrons. Okay, that's it. Again, pretty simple. You just got to basically keep track of the different terminology. So, all right. So last thing here to talk about, well, not last thing, but one of the last things is isotopes. So I mentioned at the very beginning of these notes that atoms, even of the same element, are different from one another. And these are called isotopes. So isotopes are atoms that have the same number of protons, which means that it is the same element. Okay, so let's put this in red. So the same element, but they have different numbers of neutrons. So think of it like apples, right? There's tons of different types of apples. There's Honeycrisp apples, there's Fuji apples, there's Granny Smith apples, there's Brayburn apples, right? There's like all these different types of apples. All of them, of course, are apples, but each one is a little bit different, right? Like one's green and one's red, and one tastes sweet, one tastes a little bit more bitter. It's kind of like that, right? Atoms, even of the same element, are slightly different from one another. So the number of neutrons that are in their nucleuses are different, but the number of protons are the same because they're the same element. So they have different mass numbers. And here's an example. So here are 3 different isotopes of a neon atom. We have neon 20, and the 20 written here is the mass number. So that means that the mass of this isotope, this atom, is 20. There are 10 protons, because that is the atomic number of neon. That's what makes it neon. And there are 10 neutrons. Adding those together, you get a mass of 20. Then we have neon 21. Again, it has 10 protons because that's what makes it neon, but this time there are 11 neutrons. So it has one more neutron than the previous atom, in which case it's a little bit heavier, and we call this neon 21 because if we add those two together, our mass number is 21. Then over here we have 12 neutrons in this atom, and so this is neon 22, but the protons are still 10. Okay, so each one of these will still behave like neon. It will have the same chemical properties. The difference is that it will be a little bit heavier, okay, which can have an impact on some different things that we're not really going to get into. But okay, so here is a problem, and again, we'll erase this little picture so you have some space to type and do some writing. It says diamonds are a naturally occurring form of elemental carbon. Two stable isotopes of carbon are carbon-12 and carbon-13. Write the symbol for each isotope using superscripts and subscripts to represent the mass number and the atomic number. So what this is basically wants us to do is it wants us to write isotope notation, which is this. Okay, it wants us to write this for carbon-12 and carbon-13. So we're going to need to know the element symbol, the mass number, and the atomic number for us to do this. Okay. Now, if you don't have a periodic table on hand, I'm going to give you the symbol for carbon, but you would need to look at the periodic table to find the symbol for carbon, as well as to find the atomic number for carbon, okay? But I know them off the top of my head. So, all right, so we are going to have a C for carbon, and we're going to have two C's because we're going to write two different isotope notations here. Now, we have there's little hotkeys to do superscript and subscript. But otherwise, if you go to Format, Text, and you go to Superscript, this will let you write numbers up above. Sorry, let's try this again. Format, Text, Superscript. There you go, like that, okay? So you write numbers up above. That's what we call a superscript. It's like exponents in math. And then we also can go Format, Text, Subscript, and that will then put numbers underneath. So in this case, our number down below would be a 6 because the atomic number for carbon is 6. If we find on the periodic table, its atomic number is 6. So it's going to look something like this. And let's actually make this a little bit bigger so that we can actually see this better. Okay. So this is what they're asking for us to do. Is they want us to write our symbol or our notation like this. So carbon-12 would look like this. As for carbon-13, again, we'll go Format, Text, Superscript. We're going to have 13. Oh, we got to make the text, I think, the same font size. There we go, 13. And then we will go Format, Text, Subscript, 6. Okay, so the mass number for each of these are 12 and 13 respectively. And the atomic number for both is 6 because that is what makes each one of these a carbon atom. Okay, and again, the atomic number can be found on the periodic table. And just to show you here, I'll even Google a periodic table. And I'll show you even where we can find it. It doesn't really matter, I guess, which one we look at. Let's just click on this first one. Okay, so here's a periodic table. And carbon is this box here. And we're going to notice there's a 6 up in the upper left-hand corner. Or over here, it shows a bigger version. This here is our atomic number. Okay, that tells us how many protons there are. So on your periodic table, which you have on your Schoology as a PDF, it's going to have the same thing up in the top. So, all right, these are our answers. That's what they're looking for. So, okay, last thing here to talk about is atomic mass. So each isotope has its own individual mass number, but when you take a sample of all of these elements, of like one element, let's say for example I had a sample of carbon, okay, which is basically charcoal. There's going to be 3 different isotopes in this sample, and if I wanted to know the mass of just one carbon atom there, it could be carbon-12, it could be carbon-13, it could be carbon-14. Each one's going to have a different mass, and you'll notice on the periodic table that there's only one number written here, and this is what we call the atomic mass. So this is on average how much one carbon atom weighs, and it's a decimal. This number is an average mass of all of the different isotopes that exist for carbon. So we need to be able to determine, well, how do we calculate an average mass? Now, atomic mass is given in a fancy unit called atomic mass units, okay, AMUs. It's determined based on a carbon-12 isotope, which isn't really that important to understand for right now, so don't worry about that. But the main thing to note is that every element has some number of isotopes, okay? And each one has a different mass. So like, for example, let's look at carbon. There's carbon-12 and carbon-13. There's also carbon-14, but they're not showing it on here. And the mass of carbon-12, of course, is 12. The mass of carbon-13 is technically a little bit larger than 13. It's 13.003. But if you average these out using their percent abundance, you'll get an average of 12.011. Now, what they're doing here is they're basically taking the mass of each individual isotope. They're multiplying it by an abundance, which is basically a percentage of how frequently you will find these isotopes in nature. So even though each of these elements has multiple isotopes, some of them are more common than others, right? So for carbon, if you went out and had a big pile of carbon atoms, 98.89% of them would be carbon-12 isotopes. Only 1.11% would be carbon-13, which means if you were to average these out, on average, the weight of one carbon atom is going to be much closer to 12 than it is to 13, because carbon-12 is much more commonly found. So it has a bigger impact on the average. Okay, it's what we call a weighted average. So the atomic mass is a weighted average of all of the isotopes that occur for that element. And what we do is we take the mass number of that isotope, we multiply it by the relative abundance, which is a percentage. Okay, and that percentage would need to be given to you, or you need to have some kind of, reference table to look at. On this table here, they're giving us these abundances. That's what these numbers here are in the middle. But it's a percentage, you multiply them together, and then you add them all together, okay? So this is one example here where let's say we have 4 atoms of chlorine. And chlorine, in this sample, there are 3 isotopes of chlorine that are chlorine-35, and there's 1 isotope of chlorine that's chlorine-37. So we could add the masses of these chlorine isotopes together. So we have 35 plus 35 plus 35 plus 37, and then divide this by 4, which is the total number that we have in the whole sample. And they show the math down here, and we would get 35.5 as an average mass. And it's closer to 35 than it is to 37, because of the 4 isotopes shown here, 3 of them are chlorine-35s, 1 is chlorine-37, which means on average, if you consider how many 35s there are compared to 37s, your average will be closer to 35. Okay, that's why there's decimals on all the masses of all the elements on the periodic table. Right? If you look at nitrogen, 14.007, oxygen, 15.9999, right? All that stuff. So, all right, so let's take a look at another practice problem here. Again, let's delete this picture. And I think this is the last one. So it says, the atomic mass of copper is 63.546 AMU. Which of copper's 2 isotopes is more abundant, copper 63 or copper 65? Now this one, we actually don't even need to do any math to solve this, because all we're going to do is we're going to look at the average. So on average, okay, the average mass is 63.546 AMU. That's the average. We have 2 isotopes, copper 63 and copper 65. If the average is 63.546, that means that it is closer to 63 than it is to 65, which means that copper 63 would be more abundant because it has a bigger impact on the average. That's why the average is closer to 63. If this average was like 64.5, then copper 65 would be more abundant because the average is closer to 65 than it is to 63. Okay, so we can say that copper 63 is more abundant because the average atomic mass is closer to 63 than it is to 65, which means that copper 63 has a bigger impact on the average. Okay? All right. So to calculate our atomic mass of an element, what we want to do is we're going to take the mass of each isotope, multiply by its natural abundance as a decimal, and then add them together. Okay, now here's an example. So Carbon-12, for example, has a natural abundance of 98.89%. Carbon-13 has a natural abundance of 1.11%. If we wanted to know what is the average atomic mass of just carbon, we would take 12 AMUs, which is the mass of carbon-12, times 0.9889, which is 98.89% as a decimal, plus 13.003 AMU, which is a more precise mass for carbon-13, but this could just be 13, it'd be fine, times 0.0111, which is 1.11% as a decimal. If you add those together, you'll get an average of about 12.011. All right, so let's take a look at another example problem here. So it says element X has two natural isotopes. The isotope with a mass of 10.012 AMU, which is, isotope X10, has a relative abundance of 19.91%. The isotope with a mass of 11.009 AMUs, or X11, has a relative abundance of 80.09%. Calculate the atomic mass of this element. Okay, so here's what we're going to do, okay? So we're going to go 10.012 AMUs, that's the first isotope, times its abundance as a decimal. So 19.91% is 0.1991, okay? That's how we express it as a decimal. And then we're going to do that plus the next one. So the next element isotope is 11.009 AMU times its abundance, which again is a decimal, 80.09% is 0.8009. And then those are the only two that were given. So if we do this math out and add them together, we will get an average that is probably, in this case, going to be closer to 11 than 10, because this one has about an 80% abundance and the other one's only 20%. So it has a bigger impact on the average overall. But let's do the math out here. So I'm just going to use my phone as a calculator. 009. All right, and I get, and I'm going to round, I guess, to 5 significant figures. Or I guess we'll go 4 significant figures because of the percentages. So 10.81 AMUs would be the average atomic mass. And again, if we look at that, we'll notice 10.81 is closer to 11 than it is to 10, because this isotope, isotope 11, has an 80% abundance. So it has a bigger impact. The average is going to be skewed towards 11 than it is to 10. So, okay. The last thing here to talk about is just the periodic table and how things are set up. So this is going to be just a real quick synopsis. We don't have a whole chapter on the periodic table, so it's just a real quick preview. So the periodic table is arranged in columns and rows, okay? Vertical columns, horizontal rows. And it's set up in a lot of different ways, but mostly it's set up to compare chemical properties, okay? So vertical columns are what we call groups, and horizontal rows are what we call periods. So a periodic table has elements that are all in the same vertical column that all have similar chemical properties. Okay, we call these groups of elements. So like column 1 is group 1, column 2 is group 2, column 3 is group 3, and so on. As for horizontally, okay, we call these periods. And the properties of elements within the horizontal rows don't really have any kind of relationship a whole lot. So they're just kind of arranged that way for their own purposes. But the main things are the vertical columns. So you might hear me refer to groups and periods. If you hear those words, that's what that is, okay? So elements that are in like period 4, for example, are elements of all over the place. They don't really have anything in common. But elements in vertical columns, groups, will have similar chemical properties. Okay, so like elements here in group 2A, these are what are known as the alkaline earth metals. They have a special name. And they all share a very special chemical property in the fact that if you were to drop water on them, they would explode. Okay, they're very explosive in water. In fact, all the elements in group 1A here are the alkali metals, and they also are very explosive in water. So actually these two columns share chemical properties. But the group 1A elements are more explosive than the group 2A ones. So you'll also like notice other ones. So like, for example, Ag is silver, Au is gold, and Cu is copper. These three elements are all in the same group, and they all are typically special metals or expensive metals that are used in jewelry and such, right? And that's because they all share a very similar chemical property in the fact that they're very chemically resistant. So if you make jewelry out of them, you're not going to have to worry about them like rusting or corroding over time or anything along those lines. So again, they share similar chemical properties. So, all right, anyway. So that is it for this section. I know there was a lot of information. Most of it, though, was on isotopes. There's some practice after this, of course, as always. But if you have questions on things, please make sure that you ask. So, all right, guys, that's it for this one. Thanks for sticking with me. I'll see you in the next.